Okay, welcome everybody, and thank you for joining us on our second annual UC Santa Barbara Natural Reserve System virtual seminar series. We're so glad to have you here again tonight. This was a very popular series that we put on for the first time last fall, and we had so much positive feedback that we decided to do it again. Just a quick introduction. My name is Marianne Whitman. I'm the Executive Director of the UCSB Natural Reserve System. And the UCSB Natural Reserve System is part of the UC-wide Natural Reserve System, which has 41 sites distributed across the state of California with protected lands expressly for research, education, and public service. There's really nothing else like it in the world. UCSB manages seven of these reserves. And for this series, you will be able to join us on a tour of all seven of our reserves to learn from the researchers, the educators, and the reserve directors about what we do here at our sites. Tonight, we're going to start on the Eastern Sierra. We're going to head east and north of Santa Barbara, if that's where you are, with the Sierra Nevada Aquatic Research Laboratory Reserve. Before I turn it over to our reserve director, Dr. Carol Blanchette, who will tell us a little bit about SNARL and also introduce our speaker, Dr. Ned Bair. I wanted to just take care of a few housekeeping items. I think everybody's pretty good these days at handling Zoom and Zoom webinars, so this will be probably not news to you. Our format tonight is that we'll first hear from Dr. Carol Blanchette, our reserve director at SNARL, for 15 minutes, and she'll tell us a little bit about the reserve and give an introduction to our speaker. Then our main show for tonight, Dr. Bair will speak for 30 minutes about his research that he conducts out of SNARL. And then at the end, we'll have a Q&A session, and this will be for 10 minutes. And this is a chance for you all to ask us any questions that you have for either our speaker or for Carol about the reserve. To use this function, if you look at the bottom right hand of your screen, there's a Q&A button, and you can type in your questions there. And then I will moderate the Q&A, and I'll select the questions for our speakers, and we'll find out more at the end of this. So last item is that this will be recorded, and this will be available tomorrow on the UCSB NRS YouTube channel. So if you couldn't catch all of it tonight, or if you want to share this with everybody, this will be sent to you in a follow-up email so you can find it pretty easily. And with that, I'll turn it over to our reserve director at SNARL, Dr. Carol Blanchette. Carol?
Great. Thanks, Marianne. Welcome, everybody. Thanks for joining us tonight. I'm going to just share my screen here so you guys can all see what I'm talking about. How's that? Good? Okay. So as Marianne mentioned, the Natural Reserve System consists of 41 sites that are spread across the state of California. 7 of those are managed by UC Santa Barbara. So today we're going to visit one of the sites that's the furthest away from Santa Barbara, up here, number 36, and lies at the heart of the Central Sierra Nevada mountains. This is the Sierra Nevada Aquatic Research Laboratory, and we refer to this as SNARL. So if you were to take a road trip from Nevada and you were driving to the west, you would run directly into these mountains. This is the Sierra Nevada mountain range. SNARL lies directly at the base of Mount Morrison, right here where the star is. And so we sit at about 7,500 feet in elevation. Just to give you a little history of SNARL, SNARL actually started out as the U.S. Fisheries Bureau research facilities in the 1930s. So here was pretty much the extent of the field research station back then. It was known as Convict Creek Experiment Station, and the focus of that work was really the emerging trout fishery. The work focused largely on the behavior and the survival of these introduced trout in natural streams. Ironically, today, much of the research at SNARL still focuses on this, but however, more on the ecosystem impacts of these trout introductions and the consequences for many of the Sierra native species. So this was the entire field station back in 1940. And you can see here our iconic Mount Morrison in the background. Years later, SNARL became part of the Natural Reserve System of the University of California in 1972. So here we are 80 years later. This is an overview shot of SNARL. And since then, SNARL has grown to become one of the largest and most productive field stations in the UC Natural Reserve System. For those of you familiar with Mammoth, SNARL lies on Convict Creek, seen here, and just below Convict Lake, which is off the screen. It's also very near to the Mammoth Yosemite Airport, which is up here. So at SNARL, we like to think that the Sierra Nevada mountains are our backyard and the Great Basin is our front yard. It's literally a high elevation base camp for researchers working in both of these environments. So I'm going to show you a short video that just highlights SNARL's significance as a field research station.
The Sierra Nevada Aquatic Research Laboratory, known as SNARL, is a unit in the UC Natural Reserve System administered by UCSB. SNARL is a 56-acre site, but that understates its significance. Because we're nested in an area that's almost entirely public land, we have access to millions of acres of Forest Service, National Park, wilderness. I view it as sort of a portal reserve, a stepping off point into all that area of public land. So it's a much more important, significant site than its 56 acres belies. And it's one of the most heavily used and active and productive sites in the Natural Reserve System.
Well, the UC Reserve System is so important because I think what they provide are these natural outdoor laboratories. And if you go to any of the main campuses in the UC system, there are very high-tech laboratories at many of these sites. But a lot of times, if we want to understand what's happening out in the ecosystems where those things are happening, we need to have the capabilities of laboratories and facilities there where we can actually house researchers and where they can bring samples back and process them immediately.
Having a facility like this in a relatively remote location really allows me to do the work that I do. After we finish a survey and we discover that a particular frog population is doing really well, within a matter of a week or two, I can have a helicopter arranged through Yosemite National Park to help us move some of those frogs to a different location. Without having a central base of operations like SNARL, I could never do that.
Okay, so our summer season, which you've seen here at SNARL, is often the busy season. And there's a lot of university classes and researchers that come. And I would say the most frequently asked question that I get is if it snows here in the winter. And I think this picture provides evidence that it indeed does snow here in the winter. We are indeed open year-round, and we actively support a wide range of research that happens in all the seasons. Just to give you a glimpse of some of the research areas that we support at SNARL, and although the A in SNARL is aquatic, the research here is not just aquatic. We support a wide range of field studies. Certainly Ned tonight will be talking about climate and snow and hydrology. However, we support a wide range of research in geology, all the biological sciences, conservation, as well as emerging research in the fields of disease ecology, as well as the humanities. So researchers come here and have worked on photography, writing, sculpture, and the arts. At SNARL, we're also the base camp for several large research projects. One of the large groups that works at SNARL is called the Mountain Lakes Research Group. And the focus of their work is really addressing the management challenges in the aquatic ecosystems of the Sierra using science. The focus of much of that work is on the ecosystem impacts of introduced non-native trout in the lakes of the High Sierra and the conservation of this particularly adorable amphibian known as the mountain yellow-legged frog, one of my favorites. SNARL is also the home for a new consortium focused on snow science, hydrology, and climate change impacts in cold mountain environments. This partnership involves UCSB researchers, as well as those from Nevada's Desert Research Institute and the US Army. And Ned will be talking a little bit more about that tonight. And the acronym for this group is ICE-CREAM. ICE-CREAM is going to be based at SNARL and will serve as an interdisciplinary hub for collaborative research and education focused on scientifically and economically driven questions about water supply, storage, wildfire, and biodiversity in the Sierra Nevada. So like all of the NRS sites, SNARL's facilities support education, research, and public service. So SNARL has a dormitory as well as multiple other housing facilities to support use by university classes. SNARL is also the home to a new NSF-funded program that will expand opportunities for students from diverse backgrounds to participate in the environmental and conservation sciences. We all know that children are our future, and investing in high quality educational experiences is vital to sustaining our environment and our economies. So every day in May and early June, a busload of kids in grades K through 6 arrives at SNARL for grade-specific lessons. And these range from natural history lessons to activities in archaeology and Native American life skills. A lot of our programs, as you can see here, also combine science and art. So we have a small education staff and a core of volunteers that help to run these programs. We host over 2,000 children from across Inyo and Mono counties each year for these elementary school field trips. And unlike Santa Barbara, these counties are really remote and far from any science centers. Our programs are all supported by donations to the reserves. So we absolutely rely on this support, no matter how small. And we invite you to join our community of supporters if you're interested in keeping these programs going. At SNARL, we are also passionate about connecting people of all ages to science. And one of our signature outreach programs is the SNARL Seminar Series, where we host researchers to come and give scientific talks on topics of local interest. So the seminars run every Tuesday evening from early May to mid-June at our newest facility at SNARL called the Page Center. In a normal year, these events are a great way for our community to come together, and we often have music, food, and drinks. And we were really looking forward to getting back to this beyond the COVID times. SNARL, as you can see here, has facilities that are on par with a small college campus, including a modern laboratory, housing for classes and researchers, and high-speed internet. Sustainability lies at the core of our mission, and 7 different solar arrays meet the majority of our needs for electricity. Our newest facility you can see here in the foreground is the Page Center, and this is a state-of-the-art classroom and meeting space. It's also the first zero net energy facility in the UC system. One of our most unique research facilities is a set of 9 experimental stream channels. These were designed to serve as identical replicates of streams and are fed directly from Convict Creek. And researchers over time have used this system for studies on stream ecology, hydrology, and fisheries. And last but not least, another unique facility is the Snow Science Laboratory, which is operated in partnership with the US Army Cold Regions Research and Engineering Laboratory and UCSB. So for those of you who like to ski at Mammoth, this facility lies right near the McCoy Lodge, shown here with the red star, and it transmits real-time data and images to UCSB. Snow is a critical resource for the state of California and forms the majority of the water needs for the state. Research ranges from forecasts of water availability done by mapping snowpack from aircraft to the design of sensing systems for vehicles to navigate in snowy and low visibility conditions. So on that note of snow, it is my great pleasure today to introduce our speaker today, Dr. Ned Bair, seen here in his native habitat. Ned is one of the lead SNARL snow scientists in the ice cream group, and he's also a research scientist at UCSB's Earth Research Institute. Like us, he lives here in Mammoth Lakes, and his laboratory is in the snow-covered mountains of the Sierra Nevada. Ned received his PhD from UCSB in 2011, and he has authored dozens of scientific papers on snow science and hydrology. He has worked as a mountain guide and a ski patroller at Mammoth Mountain since 2012, and he specializes in remote sensing, spectroscopy, and the energy balance of montane regions. Ned's presentation today will focus on how we are darkening Earth's snow and ice, and the impact on global climate, and a brief pause during the COVID-19 lockdowns. So Ned, I'm going to turn it over to you.
Okay, well, thank you for that introduction. I'm going to share my screen. Can let me know if you see it. Okay, can you see that? Does that look okay?
Looks good.
Okay. Okay, well, thank you, Carol, for that introduction, and Marianne for organizing this. And, you know, I was looking over the attendee list, which I guess some of you on the webinar maybe can't see, but we can see it as speakers. And it's, I see a lot of familiar names. So thank you for sharing your evening with us. And I see a lot of people I don't know. So that's exciting. And of course, this would be nice to be giving this talk in person, but you know, it's depending on where you are. If you live here, you'll know that the air quality is terrible right now. And so I've been up actually at Q's all day, our energy site on Mammoth Mountain, and I would smell like an ashtray. And you know, it's maybe better for a virtual format right now, all things told. And also I can attest that it definitely does snow at SNARL. I lived there in the winter of 2009. And, you know, we had a couple sort of tear-filled drives back with my wife and I from town, you know, or like the Millennium Falcon going into hyperspace. You know, I can't see anything. So it's a rugged place, but you know, a great base, as Roland and Dan and Carol talked about. Okay, so I'm going to talk about how, got a lot of stuff on my screen here. How we are darkening Earth's snow and ice and the impact on global climate, with a brief pause during the COVID-19 lockdowns. I'd like to thank my co-authors for this work, Timbo Stillinger, Carl Rittger, and Mackenzie Skiles. Timbo's at UCSB and is also a researcher at ERI, the Earth Research Institute, where I am. Carl Rittger is at CU Boulder, and Mackenzie Skiles is at the University of Utah. Now that's a picture of me at the North Peak Ice Gully, and that's over by Mount Kinest, you know where that is, just outside of Yosemite. And these, you know, these ice couloirs are disappearing. And you know, one thing you'll notice about it is how dirty it is, and that's sort of what the snow surface looks like in September right around now. And you know, a lot of that is dust, but some of it's soot, and it has a big impact on the snow energy balance, and that has global implications, which is what I'm going to talk about. So I've been told to put a slide in about my, you know, how did I wind up studying snow and living in Mammoth Lakes? Well, you know, to my parents' dismay, I graduated from college. I went to Bowdoin College in Brunswick, Maine. You know, go Polar Bears. I became a ski bum pretty much. I went out and I worked as a patroller at Mammoth for a decade. I also worked as a alpine rock and ice guide in the Cascades. I did along the way earn a PhD in environmental science and management at UCSB in 2011. I did a dissertation on storm snow avalanches. After that, I worked as a postdoc at the Army Corps of Engineers Cold Regions Research and Engineering Laboratory, who have graciously supported not just me, but our site Q's for going on 30 years. I've been on the research faculty at UC Santa Barbara at the Earth Research Institute since 2012, and I work primarily on remote sensing projects, so spaceborne imaging of snow and sometimes snow avalanches. And here are a few pictures. That's me in the grinning there with the beanie on, guiding a group up to the summit of Mount Hood up in the upper left. Upper right corner is me. That's Scotty's in 2007. That's about an 7 foot crown face from a large persistent layer avalanche. Something we don't see here very often. Really weak snow. Didn't snow that year until February, and that's when that happened. Lower left corner, that's me skiing down from 17,000 feet on Denali in Alaska. And then in the lower right, that's me in the Indian Himalaya, digging some deep pits, snow pits, which has been kind of a theme in my work. Okay, so since this is Zoom, and I've also been told that for science talks in general, you should just put your conclusions and your results first, because some people may not care about the sort of intricacies of how you got there, right? And so let's try to keep your interest right. Here are the results and the conclusions. Okay, albedo is a Latin word for whiteness. Okay, and so I'll get into more of that later. But the snow albedo affects global climate, and it has very important implications for whether or not we're in an ice age. We are darkening snow and ice globally, and this is causing accelerated melt. There was a brief pause in the spring of 2020 during the COVID-19 lockdowns when, particularly in the Indus Basin, which is shown on the right, people stopped driving cars and stopped going to work for a while. So the Indus is a particularly interesting basin for pollution because it supplies water for over 300 million people, and it's heavily polluted, and there's a lot of snow and ice stored in it. So what we found is that the snow and ice was cleaner during those lockdowns by about 30%, which is significant. It changed the timing of meltwater, 6.6 cubic kilometers of meltwater. And for comparison, that would be larger than the largest reservoir in California, which is Lake Shasta, which holds about 5.6 cubic kilometers of water. And this was published in the Proceedings of the National Academies of Sciences. And you can see this is an image showing the decrease in melt across the basin, with some areas being significantly there's a lot of variability depending on how much snow and ice there is and how polluted the snow was. And there's Islamabad and New Delhi also shown. Okay, so let's take a step back, and this is called Snowball Earth. This is 720 to 635 million years ago. This is an artist's rendition from a great article in the New York Times. And my understanding is all this will be posted on YouTube on the UCSB Natural Reserve System channel if you want to go in and check out some of those links. And there's evidence that glaciers at sea level had reached the equator. Okay, so particularly paleomagnetic evidence and other things that indicate that there were glaciers, sediments, at the equator, and so it's, this is a little bit controversial, but it's clear that Earth has been mostly covered in snow and ice before. Why did this happen? Well, part of it can be explained by orbital variations and axial variations. So changes in, how the Earth orbits the sun, its eccentricity, its, precession, things like that. And those are well understood. They're called Milankovitch cycles. But there's also this runaway snow albedo effect. And I'm going to get into what that is. What is the snow albedo effect? Why is snow albedo important? So snow on present day Earth, even during this interglacial period, okay, that means in between ice ages, which is where we are right now, snow covers a significant portion of the Earth, especially in the winter, right, in the Northern Hemisphere. And so what I've got is a video from this great NASA product called Blue Marble, where they're able to piece together imagery. In this case, it's from MODIS, or the Moderate Resolution Imaging Spectrometer. It takes daily images of Earth, and they're able to remove all the clouds, so you can really see what's going on the Earth's surface. So this is starting out in December and playing for a year and going all the way, starting in January and going all the way through December. So you can see, that there is all of Antarctica, of course, which is a little bit skewed here, but the entire Northern Hemisphere, or there's a significant amount of snow covering the Northern Hemisphere, right? So this has implications for our climate. Okay, so what is the snow albedo feedback? Snow is the brightest natural substance in the visible spectrum. Okay, that's why it's white. Now that is where most of the sun's energy is. So most of the sun's energy is reflected back with snow cover. And we know from snow hydrology work, particularly Danny Marks and Jeff Dozier's work over in the Tokapa Basin, which is on the west side, a little south of SNARL, that solar radiation dominates the snow energy balance in most mountainous parts of the world. Its whiteness, which is, as I said before, the Latin word is albedo, reflects most of the solar radiation. And what that is it's the reflected solar radiation divided by the incoming solar radiation. Okay, and because the Earth, the area covered by snow on, because of its area, because it covers a large area, snow albedo really affects climate because of that reflected solar energy. Now, the snow albedo feedback, I'm going to go into it a little more, but I want to point out this how snow looks different from other substances. Okay, so here's snow, and you can see the reflectance going from 0 to 1. So 0 being black, say, and 1 being really bright. In these visible wavelengths, okay, which is this area here, kind of from the left edge of the graph up to about 0.75, it's almost near 1. And other substances like vegetation, soils, they don't look like that. Okay, and then it has this interesting characteristic where it has these absorption features, these little drops, and then it decreases as the reflectance decreases as you get into longer wavelengths. Not too many substances look like that, okay, where you have something that's really bright in the visible wavelengths and then gets darker in the longer wavelengths. You can see that, soil just sort of increases in brightness as you get into the longer wavelengths, and vegetation has this, it's pretty dark actually in the visible wavelengths, and then has this red edge where the reflectance really goes up so plants don't overheat and stuff. And we can use spaceborne imagers like MODIS, as I talked about earlier, to figure out what we're looking at, because it has bands, and those are sensors in those different wavelengths. Okay, bands 1 through 7 are shown, and you can get an idea of what you're looking at by looking at all those bands simultaneously. And that's called spectral mixture analysis, and it's what we do to map the snow cover. So the snow albedo feedback, have you noticed how it's colder after it snows? Well, one of the reasons is because of the snow and ice albedo feedback. Okay, that air is actually being cooled, okay, because not as much solar radiation is being absorbed. There's also, you know, typically here a cold front that comes through, so that's part of it too. But the idea is you have this, you can have this feedback mechanism. That's sort of a loop, right? Is a feedback. And one way you could have a cooling feedback. Okay, so for some reason you get increased snowfall. Well, that leads to increased snow cover. That would lead to less solar radiation absorbed. That would lead to cooler air temperatures. Okay, and those cooler air temperatures mean more precipitation is going to fall as snow. So that's a cooling feedback. And you can also have a warming feedback where you have, for some reason, decreased snowfall. Well, that means you have decreased snow cover. That means more solar radiation is absorbed. Then that means that you have warmer air temperatures. So you're going to get less snow because now your air temperature is warmer, and you're going to have, you know, say more rain than snow. So that's a warming feedback. So that, in a nutshell, is what the snow albedo feedback mechanism is and why it's important. So our climate is quite sensitive, as I said, to snow albedo. James Hansen, who really launched climate change advocacy in the 1980s, and there he is testifying in front of Congress, finds that a small 1.5% to 3% decrease in snow albedo over the northern hemisphere is twice as effective at raising global air temperature compared to a doubling of CO2. And that's a little bit of a mouthful, but the doubling of CO2 is sort of the standard so-called efficacy that various forcings are compared to, right? So it's a small drop in snow albedo can have pretty dramatic climate consequences. But snow albedo is really hard to measure. Well, it's especially hard to measure in the mountains, which is what our research group is really interested in. And why is that? Well, because we have mixed pixels, okay? And Dave Selkowitz has a great paper on that, showing that in the mountains, basically all the pixels are mixed. And what do I mean by a mixed pixel? A mixed pixel, if you look in the lower right there, you can see a scale bar from 0 to 30 meters. Okay, so that's Landsat scale. That's a pretty fine resolution instrument. There's all kinds, this is Big Margaret Lake, if you know what that is. There's all kinds of stuff there. There's snow, there's rocks, there's shadows, there's trees. In other words, you're never just looking at snow, you're looking at all kinds of other stuff. And so you have to figure out a way to deal with that. And that's where the spectral mixture analysis comes in that I alluded to earlier. You can have uneven surface topography, okay? So on the lower left there, those are called, most commonly called sun cups. More technically, they're called ablation hollows because they're not always formed by the sun. But there are these features where the snow surface is really uneven and it forms these cups, and it's a drainage feature that happens in the spring, and that causes all kinds of shadowing and stuff that's difficult to deal with. There's also obfuscation from clouds. That's something that Timbo Stollinger spent his PhD working on. And snow cloud discrimination in general is just a problem that's plagued remote sensing. And then there's trees, okay? And there's a lot of snow in the trees and under the canopy. And frankly, we make guesses about that because it's really hard to tell what is down there unless you have something like a laser scanner. And you know, there's nothing in space that is good for mapping snow under the canopy everywhere, for instance. And there's a lot of snow under the canopy in the Sierra Nevada in particular. So there's different sources of snow darkening, right? So not only do we want to, measure the snow albedo, but we want to know what's causing that darkening. So all of the sources below can darken the snowpack, but they affect different parts of the spectrum. And that's that chart I was showing you with the increasing wavelengths over there on the horizontal axis. So down here in the lower left corner, this is 49-day-old snow. And that's a scanning electron microscopy image that I took as a PhD student. So that's a great way to look at snow, because it really shows the 3D structure of the snow, and it's not using visible light. So and the magnification is obviously very high. So, but that's what old snow looks like. It's not really rounded, but it's kind of round. Then we have dirty snow in the middle. Okay, that's from a paper by Mackenzie Skiles. That's showing, this is San Juan dust. It's a dust storm from dust coming off the Colorado Plateau. Has pretty dramatic implications for their water supply. And that's a picture of a isolated column that's dirty, surrounded by clean snow. And then there's shaded and sunlit snow, right? There's all kinds of issues with shadowing, and so there's a picture from some field work that Timbo and I did in the Indian Himalaya, and there's our manual transmission, no power steering Jeep that we rented, and you can see just a little bit of sunlight on this peak here, right? And everything else is in the shade. Well, that's really difficult to deal with from a satellite. Okay, so when I'm talking more about wavelengths and the electromagnetic spectrum and all that, I know that this, I don't want to make it too confusing, but we're talking mostly about this sort of visible and maybe into the infrared a little bit. That's where all of my work is, okay? These other wavelengths, there's all kinds of things you can do with them. In terms of science, but I'm not going to talk about that, like, radars and microwaves, stuff like that. So this albedo concept, right? What does it look like for different types of snow? Okay, so here in blue, we have clean new snow albedo, okay? And that's, what I mean by clean is no pollutants. And what I mean by new snow is I mean small grains. That's what snow tends to get bigger as it ages. So it's really bright. It's the brightest, okay? Now, the second curve here, you have clean old snow, okay? So the only thing that's changed is the grains have gotten bigger. And you can see that it really decreases in reflectance, especially as you get into the longer wavelengths. Okay, you move to the right. Then there's dirty old snow, okay, which sounds kind of funny. But the important point is that all of that, the effect of the impurities in the snow, the soot, the dust, it's all happening in the visible wavelengths. Okay, so maybe a little bit in the near infrared too, up to about this 1 micron area. So if we have a sensor that sees at multiple wavelengths, we can start to figure out, are we looking at changes due to dust and dirt, or changes due to metamorphism, or both? And then down in the bottom, we have dirty and shaded old snow, which is often what happens. You have snow that's not just polluted and has dust and soot on it, but it also has, say, all these sun cups and other things that are causing shadowing. And what's interesting about that is that drops the reflectance or the albedo in all the wavelengths. So you can see it's sort of just shifted down from the dirty old snow curves. Okay, soot and dust. So soot, and what I mean by that is black or brown carbon. and that depends on the temperature that it's burning at. That can be natural from wildfires, or it can be human-made, right, from fossil fuels. Turns out that, sadly, I guess, soot is found in snow everywhere on Earth, except for maybe some remote parts of Antarctica. And it's even found there, but it's in quantities that are maybe too small to affect its albedo. The good news is that ice core records show that soot peaked during the Industrial Revolution. That was when we were doing, the most coal burning and things like that. So that's clear. That's in the ice core record. And Dan McConnell has a nice paper on that from an ice core in Greenland. Dust is considered a natural pollutant, but it's practices like overgrazing and other human effects increase dust loads. So it's not, there is a human caused element. Dust tends to accumulate on the surface in the spring and is often the predominant pollutant in montane snowpacks. Okay, and so that picture of North Peak I was showing you, most of that dust is local, and that's what the main pollutant is on the snowpack. It's dust from non-snow covered areas, but there's also other stuff in there, from the Central Valley and soot. And one problem with soot and dust is that they can be spectrally inseparable. Okay, and here's a publication showing the two curves up in the right there. You can't tell the difference, even with a very good spectrometer, between dusty snow and sooty snow of certain types. Now, there's a small error there, and this is just taken straight from the paper, so I'll give you a prize if one of you snow hydrologists who I know are here wants to point that out to me. Okay, so back to the COVID lockdowns in the Indus. When the lockdowns started, we had a dramatic drop in, this is aerosol optical depth, but it's what that is a measure of is how clear is the air. It got really clean in places like New Delhi, Kathmandu. You can see the Himalaya for the first time in recent memory. I mean, if you've ever been to Delhi, it's pretty hard to see the ground usually when you're flying in because the air pollution is so bad. And there was one tweet I remember of a guy who had an air filtration system, kind of like what some of us are running now in town here in Mammoth Lakes. And he said it was always yellow, but it actually turned green during these lockdowns because it could keep up, and his air was clean in his house. So I thought this would have an immediate effect on the snow, specifically its albedo, but it might be tough to see it compared to just the aerosol optical depth, for instance, because it takes time, and to not have those pollutants build up on the snowpack. Okay, so the snow cover over the Indus Basin was examined over the past 20 years, and we used two models from the moderate resolution imaging spectrometer, as I discussed before, MODIS. And both models assume that the snow is composed of mixtures of snow and other so-called end members, or things in the scene that are not snow. Now, this is our new approach here, okay? And you can see the albedo on the y-axis there, and we have our background, our snow-free, and that's an empirical end member. That means that we're just taking a picture of that area from a satellite without snow cover. So that's what it looks like. Then you have your observed which snow-covered pixel. And then what you can do is you can fit a model. That means the computer just tries out a whole bunch of different combinations until it comes out with the best fit to tell you what you're looking at and how much snow is there and how much of this snow-free end member is there. And not only how much snow is there, but what type of snow is it? How big are the grains? And how much dust or soot is in the snow. So both models showed that the 2020 equivalent dust, and that's really just a way of saying that we can't tell the difference between dust and soot, so we just call it an equivalent dust concentration. That those levels in red were significantly below the mean, which is in black, and near the lowest levels recorded over the 20-year record in gray. And I should mention that MODIS has had over 100,000 orbits and is this amazing moderate resolution instrument that, you know, it's totally outlived its you know, by more than twofold its projected life. But we have these great records of the Earth on a daily basis going for over 20 years. And then, you know, we have uncertainty, right? So the idea here is that the width of these shaded areas represent uncertainty. And if you don't have two lines intersecting, that means they're significantly different. And we can say that, you know, it really was cleaner. And both models, they showed different amounts of this equivalent dust, but they both show significantly less pollutants in 2020 compared to the 20-year record. So Carol already mentioned ice cream, and I'm gonna briefly put in a plug for it again. You know, I heard Jerry Brown. I couldn't find this quote, but I remember him saying it once. So I'm not sure where he said it, but California has 40 million people, but not enough water. So that's a problem, right? Or maybe it has enough water in the mountains, but we can't get it to everyone who wants it. So, you know, water is a big issue, right, in California and throughout the West. So ice cream, right, the Interstate Consortium for Ecohydrology in Cold Regions Mountain Environments, which is a bit of a mouthful, is we're going to address that water crisis. And the reason why it has that, you know, cold regions, mountain, and all that has to do with our partner, the Army Corps, and some of the wording that is important to them. So we're seeking congressional funding for a joint effort between the Desert Research Institute and UC Santa Barbara to solve this crisis. And here's us in our first annual workshop, which was held on Mammoth Mountain. That's at our snow study site in this past June. Up in the upper right corner, that's in a big year, right? Remember those when it used to snow here? Well, that was 2017. And the platform, that's 6 meters off the ground. It's almost buried. So we really see quite a variation in here, you know, from maximum snow depth of around 1 to 1.5 meters to over 6 meters. That's just the nature of the Sierra Nevada. And then of course, SNARL, which Carol talked about. I know the font's tiny. These are all the references if you're interested in that. I think hopefully you can see them on YouTube. We are hiring, so if you're interested in grad student or postdoc opportunities, please contact me. If you're interested in ice cream, contact Marian. That's her email address there. And in closing, I just want to explicitly thank everyone and all the organizations who have helped with all of this work. It really it takes a village, and you know, it's I'm just grateful for all the mentorship and help I've received, and again, thanks to Carol and Marian for organizing, and to all of you for attending. Thanks.
Great. Thank you, Ned. All right. If you want to take down your share screen, Ned, then I think we'll move right into the Q&A session. So first of all, just thank you for that great talk. I had no idea there were so many kinds of snow, dirty snow, sooty snow, yellow snow, all those things, although you probably didn't talk about the yellow snow. We have some questions in the Q&A, and I'm going to go ahead and ask those. And just for everybody, please look to your Q&A button and get your questions up there. And we're going to start with a question from Cassandra Huneau, and my apologies, Cassandra, if I'm mispronouncing your name. Cassandra asks, as a current geography student at the University of New Mexico, with an interest in remote sensing and hydrology, what kind of remote sensing hydrology research is being done at SNARL? So, I think either Ned or Carol can maybe respond to this. Ned, why don't you start?
Sure. Get a drink of water. So the question is about remote sensing at SNARL, and well, that's I would say that that site that we keep discussing, CUES, it stands for the Corel UCSB Energy Site, and that is focused on remote sensing and ground validation. We take a lot of radiometric measurements, and we really have focused on remote sensing in the visible and sort of near infrared and shortwave infrared wavelengths. But we've also done work with radars. We have some active sensing systems. We have just put in 3 LiDARs today up there. Those are laser scanners for mapping the snow surface. LiDARs are going into space now. So there's a lot, and this is an amazing area to for one reason, it's clear here a lot, right? We have, well, not right now, but normally it's very sunny and we don't have a lot of clouds, right, blocking our view of the snowpack, which is maybe one reason why we focus so much on those shorter wavelengths.
Great, thank you. Okay, our next question is from Dennis Beebe, and Dennis asks, what caused the reduction of snowmelt in the Indus River COVID-19 pause example? And he goes on to say, was it the reduction of automotive pollution locally or worldwide? Even during a shutdown, we still needed all the electrical power and associated power plants, right? So maybe Ned, you can kind of elucidate a little bit more on the causes that you're observing.
Yeah, I wish I could. I think to really do that, you would have had to have sampled the types of pollutants in the snowpack or lack thereof, and have a baseline, right? And be able to say definitively, particularly with the size of the dust and the soot, you can figure out how far away it came from, okay, which is a good way of figuring out what is causing the pollution. Reduction in vehicle traffic, of course, the vehicles aren't in the Indus River Basin, up at the high altitudes, but that soot and dust gets transported from the winds, and the prevailing weather comes from the southern part of India and moves to the north, right? So even though it might not originate there, it can be transported there by a wind.
Okay, great. There's one question in here that is for Carol, and it's how do you? This goes back to some of the programming at SNARL for field trips for kids. How do you manage everyday field trips for kids? Are these scheduled ahead of time, or do the kids just show up at the gate? How many of the days are filled with visiting kids? So Carol, maybe you could talk a little bit about how you make the outdoor science and education programs work.
Yeah, sure. So we have 2 really different seasons for our program. So we have the school season when kids are in school, and we do field trips in the spring at SNARL and the fall at Valentine Camp, which is our sister reserve. And those are all scheduled directly with all of the schools in Inyo and Mono County. So Levining and Big Pine and Bishop and Mammoth and all these local schools. And so those kids come here with their particular grades. We focus on grade specific, age specific activities. So any single kid, for example, who lives in Bishop or Mammoth will come here in kindergarten, first grade, second grade, every grade, and they will do a different activity in every grade. And all those programs are aligned with the next generation science standards. And those are scheduled with our outreach and education team here. And then in summertime, we also have programs that are sort of more week-long camps. And so those are more for kids that are maybe visiting here in the summer, local children who are interested in particular topics. And so they're sort of a deeper dive. And the summer, we also have an opportunity to do dual language programs. So we do English, Spanish programs because we have a large population in Mammoth of Spanish speaking families. And so we try to offer those programs as widely as possible. But yeah, it's a large effort, and we are incredibly grateful to donors and volunteers in this area that help us out with that.
Wonderful. Maybe the next snow hydrologist will have been able to have an experience in your programs and give a talk like this someday, just like Ned. Ned, I'm going to turn back to you now. There's a couple of technical questions which I don't even understand, but I hope that you do. So first, this is a question from C. Page Hiller Adams. And C. Page asks, since you have spectra which distinguish snow types, can you use some sort of data autocorrelation to ID snow types and therefore derive albedo using data from airplanes doing spectral scanning in areas of interest? And C. Page Hiller Adams clarifies and says, airplane with spectral scanning equipment records reflectance. Spectra are used to determine snow type. Albedo derived from that. So Ned, maybe you can help us all understand maybe what the question is about. How do airplanes play a role in this process, and you know, how does that relate to the derivation of albedo?
Yeah, thanks for that question. That's a sounds like maybe you have some experience with airborne imaging spectrometers. So there's always this need for, you know, high spectral resolution and high spatial resolution, and you just can't get, and then also frequent revisit times, right? And you can't have all of those things. But with instruments like AVRIS, or AVRIS NG, okay, which is an imaging spectrometer flown on a plane that has, you know, liquid nitrogen dewars so that it can cool the detectors, you know, for those longer wavelengths aboard. You can have high resolution and so high spatial resolution and high spectral resolution. So you can really resolve those features, especially things like the absorption feature. Okay, and I didn't go into that at all, but like you can tell the grain size by the absorption feature around 1 micron and the depth of that. You know, of course, it's only good for like the time in terms of coverage. It's only good for that one time that you flew the plane over, and it's quite expensive. But AVRIS has flown over Mammoth Mountain and over the Sierra. And throughout the West, it's flown in high mountain Asia. It's part of NASA SNOAX, and there are quite a few that have been in the past and will be in the future hyperspectral instruments like AVRIS from space that we're looking forward to for being able to really get at some of these things that you need a very high resolution, spectrally speaking, instrument to do. But of course, there's that trade-off in terms of not being able to image an area very frequently.
Okay, great. Well, that's all the time we have for all of our questions tonight. I just wanted to wrap up by talking a little bit about next week's speaker. We will have a little bit of a different approach where we're going to hear from an educator, and this will be Dr. Adam Green. He's a faculty member at Santa Barbara City College, and he will talk about his work in bringing undergraduate students out to UC Natural Reserves. The title of his talk is Getting Them into the Field, Teaching in the UC Natural Reserves. So I encourage you to join us next week. And once again, thank you, Ned, and thank you, Carol, for a lovely evening. And I hope everybody has a great night. Thank you.
Thanks.